Alright, in this video we're going to do a conceptual overview of the backpropagation algorithm. I'm going to try to make the discussion calculus agnostic, and our end goal is you should be able to conceptually understand how to implement backpropagation in your own neural network models. So the first concept we need is the concept of the derivative. I'm going to introduce a intuitive related, but not exactly formally correct, concept related to the derivative, which I'm just going to call the effect. So let's say we have a function here which we've represented using this computational flow representation because it makes visualizing everything easier. So this function represents the function y equals x1 plus x2. Now the thing we're interested in is if I add 1 to x1, what is the effect of that on y? And as you can hopefully intuitively see, if I add 1 to x1, y will increase by 1. And so what we say is that the effect of x1 on y is 1. Let's change the addition operator to a multiplication. So we now have y equals x1 times x2. And let's ask the exact same question. If I increase x1 by 1, what is the effect of that on y? And again, you can probably intuitively see that if I increase x1 by 1, y will increase by x2, because we're bringing in another multiple of x2 by increasing x1 by 1. So we say the effect of x1 on y is x2. Now, neural network functions are built by composing these basic operators. So let's consider this function. We have y hat equals x1 times x2. And then we feed y hat as an input into a second operator, where our final output y equals y hat times x3. This is called composition because we are composing the two operators. Neural network functions are composition happy. The deep in deep learning refers to deep composition, so like multiple chains of composition. So let's ask the exact same question that we asked before. If I add 1 to x1, what effect is that going to have on y? And again, with multiplication we can reason intuitively, although for more complex operators we actually need calculus. But we can reason here that if I add 1 to x1, then I know that y hat will increase by x2. Now, independently, if I increase y hat by 1, I know y will increase by x3. So it stands to reason that if I increase x1 by 1, y will go up by x2 times x3. Right, because adding 1 to x1 increases y by x2, and we said that every time we increase y hat by 1, y goes up by x3, so we have multiplication of the two effects. So we might call this a series connection, and this intuition does generalize. So in general, when I have two variables connected by a series of operators, the effect of one variable on the other variable is the product of the per operator effects. We need to consider one more pattern of effect before we can tackle a baby neural network function. This is the problem of additive parallel effects. So in this network, we have y equals x1 times w1 plus x1 times w2. And we ask, if I add 1 to x1, what happens to y? The effect that x1 has on y travels along two routes. So when I add 1 to x1, the intermediate variable h1 goes up by w1, but also the other intermediate variable h2 goes up by w2. So the total increase on y is going to be w1 plus w2. So that's a general pattern. When one variable affects another variable through parallel addition, the final effect is the sum of the individual series. So let's see why it's useful to be able to calculate the effect of one variable on another variable when it comes to optimization problems. So we'll consider a baby gradient descent problem. Let's say we have y equals 4 plus x. And let's further assume, for whatever reason, we want y to equal 23. So meaning we want to find a value for x such that y equals 23. Now obviously that can be solved using basic algebra, but let's solve it using gradient descent. To do this, we'll tack on an error calculator, which will simply be the difference between y and 23, which is the current value. So note that what we want to have happen is we want e to equal 0. So if we knew the effect that x has on e, we could update x, starting from a random initialization, to make e iteratively go to 0. And when e equals 0, y must equal 23. But we know how to calculate the effect of x on e. right? So if we add 1 to x, we know that y will go up by 1. And if we add 1 to y, we know that e will go down by 1, assuming that y is less than 23. So if we assume that we randomly initialize x at 2, then we can see that y would equal 6 and e equals 17. Now we know from the effect of x on y that if I add 1 to x, the error will go down by 1, which is exactly what we want. So if I make x equal to 3, y is now 7 and the error has gone down, and we can repeat this iteratively until the error is 0. So that is the basic idea of how knowledge of the effect of one of the input variables on a target output variable can be used to iteratively solve an equation or optimize a function. Those are all the principles we need to train a baby neural net. So let's look at maybe the simplest possible neural net architecture. So we're going to have input variables x1 and x2. We're going to have intermediate hidden variables h1 and h2. And we're going to have output variables o1 and o2. And so the whole idea for our purposes is that we're going to be given a training pair of assignments to x1 and x2 and the desired output o1 and o2. So we're going to have to compute our error between the actual output of the neural network and our desired output. So again, we tack on at the end of the neural network a function graph that computes the error. Now we haven't said how to compute h1 from x1. So we define h1 and h2 and o1 and o2 exactly the same, simply as the inner product of weight vectors corresponding to h1 and the input. And similarly, o1 is the inner product of a weight vector and the intermediate variables h1 and h2. So when we draw that out explicitly, h1 is going to involve two products, w1 times x1 and w2 times x2. So we have these two intermediate product variables, and we're going to sum them, and we're going to call the output of that h1. And the exact same pattern holds for h2, just with different weights, and for o1 and o2, except o1 and o2 receive from h1 and h2 as opposed to x1 and x2. And they all have their own weights. So we have 8 weights in total. So we're going to randomly initialize all of the weights. And given that random initialization and our input vector, we can compute h1 and h2. And then given h1 and h2, we can compute o1 and o2. And then once we have o1 and o2, we can compute the error. Now, here's the big backpropagation step. We want to know what is the effect of, for instance, w1 on e. Meaning if I add 1 to w1, what happens to e? Does it go up or down? We want e to go down. So we can visually trace the effect of w1 on e. So we can note, first of all, that w1 directly affects h1 by a series connection. And then we can see that because h1 feeds into o1 and o2, the effect of h1 on e is a parallel additive connection. And this is the basic pattern of all neural networks and the basic pattern of backpropagation. So let's actually go through the computation for w1. So we can see that the effect of w1 on p1 is x1. The effect of p1 on h1 is 1. And we have 2, so we know we're going to have a sum, right? So we know the effect of h1 on e is going to be a sum. So the first part of the sum is going to be w5, and then a 1, and this is a 1, and this is a 1. The second part of the sum is going to be a w7, and then a 1, 1, and 1. So the total effect of h1 on e is w5 plus w7. So therefore the total effect of w1 on e is x1 times w5 plus w7. And given our random initialization of the w's, we see that the effect of w1 on e is negative 1. So that tells us that we want to increase w1. Now to do a full gradient step, we would have to compute the exact same thing for all of the weights. And so the idea of backpropagation is that note that, for instance, w2 also needs to know the effect of h1 on e. So rather than calculating that twice, we simply store that somewhere, and then we avoid repeating the calculation. And that's the big idea of gradient descent, is you just work back, or backpropagation is you work backwards layer by layer to avoid repeating computation. So I hope this video gave you some conceptual insight into gradient descent and backpropagation, and thanks for watching.